Welcome to 9.3, the parabola. Seems strange that we're going to end up talking about the parabola again. Don't we know parabolas pretty well already? For example, this form or format for the equation of a parabola, you might know it as vertex form, where the vertex is located at h comma k. As a matter of fact, number 2 right here gives us a space to write in that if we're given the equation for a parabola in that format, very easy to determine the location of the vertex. Or this form, which looks like a quadratic equation to me, and it is. When we graph quadratic equations, they show up as parabolas. If the a value, that leading coefficient, is greater than 0, our parabola is going to open up like this one, and if our a value is less than 0, it's going to open concave down like that one. The x-coordinate of the vertex of, so I'm looking at number 3, the x-coordinate of the vertex of this equation is, and we can use these a, b, and c values in this equation to determine that the x-coordinate is the opposite of b divided by 2a. And when you have a function or an equation and you have an x-coordinate, you can determine the y-coordinate by plugging the x-coordinate in. So instead of this equation saying y equals, I'm going to scribble out the y equals, and I'm going to write this using function notation f of x. That makes it easier for me to write a y-coordinate, which is determined by taking the x-coordinate, negative b over 2a, and plugging it into our function. So you would do this arithmetic first, figure out the x-coordinate, and then plug whatever actual number that is into your function to find the y value. Here are some depictions of parabolas. You've got an axis of symmetry that is being depicted in green here as a dashed line. At least it looks green on my screen. And you've got the vertex. That's the equation of the axis of symmetry. I should have pointed that out, that we're seeing there and there. Here's the definition of a parabola in more like the format that we're going to be looking at it, but across the board, this is the definition of a parabola. It's this set of points that's equidistant from a fixed line called the directrix, which you may or may not have ever worked with before. So there's a directrix and a focus. And we've worked with the focus or a focus or foci, the plural of focus, in the past. And if you pick a point anywhere on your parabola, like this point P, which has coordinates x comma y, if you pick a point on the parabola, that point will be equidistant from the focus and from the directrix. And of course, that distance from the directrix is a perpendicular distance. I could also pick a point on my parabola that's right at the vertex. And this point is also going to be equidistant from the focus and the directrix. And that distance is P. It's very exciting. All right, let's go to the next page. The standard form of a parabola. Now this is interesting. This is different than the way that it was presented to us in an algebra class. Maybe we've never seen it presented this way before. This first one, this first equation, has my y value on the left-hand side, and it's being squared, which we never saw before maybe. And the result of your y value being squared, but your x value being only to the first power, is your parabola is going to be oriented concave horizontally. It's either opening to the left or opening to the right. And in that case, by our typical definition, it's not a function. Let's not get too hung up on that. The 4p that you're seeing here as the coefficient in front of x, we're going to see this in some examples, but that 4p value, the coefficient on x, is going to help us determine the value of 1p, which we were talking about as being the distance from the the vertex to the focus, or the distance from the directrix to the vertex. That wasn't much of a bracket. And very similarly with our x squared equals equation, that looks more like our traditional parabola. And again, that 4p value is going to help us determine the distance from the vertex to the focus, or from the vertex to the directrix. How is it that I'm supposed to remember that the y squared matches up with this one and that the x squared matches up with this one? That's a good question. The strategy that I use, after erasing all of the scribbling that I've been doing on here, the strategy that I use is when I look at the equation that's on the right, it has an x squared in it and it has a y to the first power, and the parabola that I'm most familiar with or the equation of a parabola that I'm most familiar with looks something like, the most basic one is y equals x squared. This parabola passes through the origin and it's concave up. Well, look at this equation. It has a y to the first power. This has a y to the first power. It's got an x squared. This has an x squared. So this equation is it's going to be the parabola that's either concave up or potentially concave down. And it becomes concave down if this coefficient in here that they're calling 4p is negative. So if your coefficient is negative, it's going to be concave down. So that leaves your horizontal parabolas leading with a y squared and an x to the first power, which is backwards from what we have worked with previously. If it has a positive coefficient, if 4p is a positive number, then it's going to be concave in the positive direction, in other words, to the right. And if it's negative, then it will be concave to the left, in the negative x direction. There is an unfortunately named component of the parabola. It's called the latus rectum. And if you worked with any of this stuff in high school, because you were of high school age, they might have called it something different, because otherwise saying the word rectum would have been very distracting. You have the pleasure of hearing the word rectum a number of times in this video, for which I can't really apologize, because it is what it is. Anyway, the latus rectum is a line. It's a line segment that passes through the focus of your parabola, and it has its endpoints on the parabola. And the total distance of the latus rectum is 4p, the coefficient on the linear factor, x to the first power or y to the first power. The fact that this has a length 4p means that the length of half of it is 2p, and the other half of it has a length of 2p also. I could have written that to the left so that I wasn't writing on top of those other notes. Alright, so that's the latus rectum. It doesn't matter whether your parabola is open and concave up, down, left, or right. It's got a latus rectum. It has a length of 4p. In math, in order to write these definitions, we have to be very specific, because if you're going to write it down, and if someone were going to dig this book up out of the ground on a deserted island and learn this stuff for themselves out of the book correctly, everything's got to be defined very specifically, which is totally fine, except I'm not going to use these absolute values. The length of the latus rectum is going to be positive, okay? The coefficient in front of the linear factor might be negative, and that's going to cause the parabola to open in the negative direction, perhaps. I'm also not going to use these really generic formats or formulas that have this negative p in here. We're going to just use our brains and draw some sketches and figure out where the things should be, where the different components should be, the directrix, concavity, length of the latus rectum, and everything's going to be just fine. However, if you want to go back into the definition and really do it by the book, you go ahead and do that. But I'm going to try to keep this a little bit less formal and still guide you to a method that's going to get you right answers. So let's check out example number 1. We want to find the focus and the directrix of the parabola. First of all, make my pen a little thinner. Is this parabola going to be concave up, down, left, or right? Well, the y squared tells me that it's going to be either concave left or right. My 4p is equal to negative 12, which is less than 0, which tells me it's going to be opening in the negative horizontal direction. Matter of fact, I think I'm going to go back, and instead of saying left or right here, I'm going to say horizontal. And the fact that our 4p value is negative, in other words less than 0, tells me that my parabola is going to open in the negative horizontal direction. And this is concavity, so write yourself a little note that what we're talking about there is concavity. The vertex of this particular parabola is going to be at the origin. Very soon we're going to work with some parabolas that are not centered or do not have their vertex at the origin, but for the moment, take my word for it, the vertex of this thing's at the origin. And we know that it's going to be concave to the left in the negative horizontal direction. Don't draw this. Don't draw this yet. I'm just drawing it that way to help us get oriented, just because I'm holding it in my mind, so I want you to see what's in my mind, or at least part of what's in my mind, but don't actually draw that yet. Also, let's take a look at the fact that 4p is equal to negative 12, which means or implies that p is equal to negative 3. Yeah, it's equal to negative 3. P, remember, is the distance to focus and directrix from the vertex. Well, if the vertex is at the origin, which we said, if the that connected very well. If the vertex is at the origin and the distance to my focus is 3 units, do you think it's going to be 3 units above, below, to the left, or to the right of the vertex? If you watched my previous videos and if you liked my analogy of the fact that the focus is sort of like the bulb inside of a headlamp, where this curve is the headlight and this is the actual bulb, so that all of our light comes out and aims at the street so that we can see where we're going. If you like that analogy, then you probably intuited very quickly to the fact that our focus was going to be to the left of the vertex, inside of our parabola. Great. If the focus is there, and just from drawing a rough sketch, I'm going to be able to tell you what the coordinates of that are, where's the directrix? I haven't said this yet in this video, but the directrix is what I think of it as being behind the parabola. So in this case, it's to the left of the parabola, and it's to the right. The directrix is behind the parabola, so in this case, it's 3 units to the right of the parabola. So I'm just going to draw in my dashed lines. The dashed line you could draw, don't draw the parabola yet. You could draw the focus, that's not going to move, but we're going to draw the parabola more accurately in a moment. The latus rectum has a length of the absolute value of 4p. I'm using the absolute value here just to remind us of the fact that we're going to refer to the lattice rectum as having a length that's positive. In this case, that's the absolute value of negative 12, which is equal to 12, which means that 2p, or the absolute value of 2p, is equal to 6. Why am I saying that? Well, let me grab my eraser, and I'm going to erase the sketch that I drew of the parabola. And in order to draw it more accurately, I'm going to plot the endpoints of my lattice rectum. So half of the length of my lattice rectum is worth 6, because 2p, or the absolute value of 2p, is equal to 6. So I'm starting at my focus, and I'm going up 1, 2, 3, 4, 5. I can't even count. 1, 2, 3, 4, 5, 6. And back to the focus, down 1, 2, 3, 4, 5, 6. Those are the endpoints of the lattice rectum, so now I can draw my parabola more accurately. Or at least I'll try. Now it is passing through the origin. A little wobble at the end there, not bad. And if you'd like, let's see, I think I'll erase this circle that I wrote around where the focus is. And then I'd like to label the fact that this distance is 2p. So is this distance, for a total length of 4p, which is the length of the lattice rectum. The directrix is the only other component of this that we haven't talked about yet in terms of, well, not specifically anyway, we drew this sketch of it. It's a vertical line that passes through an x-coordinate of 3. In fact, the x-coordinate of this point is 3, and this point is 3, and this point is 3. That's how I remember that the equation for a vertical line is, in this case, x equals 3. So a vertical line passing through all the points that have an x-coordinate of 3. So that's the equation of your directrix, and the coordinates of the focus, in this case being 3 units to the left of the origin, -3, 0. All right, let's try example number 2. Find the standard form of the equation of the parabola. Focus is there, directrix is there. I don't know, I'm still new to this, and I can't just see it in my mind, so I'm going to draw a little sketch. Directrix, well, focus, 9, 0. So that's 9 units to the right of the origin. 1, 2, 3, 4, 5, 6, 7, 8, 9. Focus is there. Directrix, x equals -9. 1, 2, 3, 4, 5, 6, 7, 8, -9. So I've got a directrix that's back here. My focus, my vertex is going to be halfway between the focus and the directrix. So my vertex is still going to be at the origin. Erase that. That's going to be my vertex. That looks like an arrow pointing down, but it's actually a V with an arrow pointing at the origin for my vertex. And which way is my parabola going to open, or concavity in which direction? Remember our headlamp wrapping around the focus. Parabola is going to be opening this way. So what about the general format for this parabola? Is it going to be y squared equals 4px, or is it going to be x squared equals 4py? Well, y equals x squared is what we know from our early learnings about parabolas. That parabola opened up in the positive vertical direction. This parabola does not open in the positive vertical direction, so I don't think it's going to be that one. In fact, it's going to be this format right here, and from there, the only component that's missing is to figure out what 4p is. From our earlier conversations, we know that p is the distance from the vertex to the focus. This is a distance of 9. I'm going to say that that's equal to p. Therefore, y squared is equal to 4 times 9 times x. So our final answer for the equation in standard form of this parabola is y squared equals 36x. Not bad. I find having this diagram so beneficial because that way I can put a bunch of information on the page. I can see how it relates to other pieces of information. I don't have to worry about holding it in my mind. And then I can write up an answer. I'm also a big fan of doing this. Anytime I can give myself sort of a skeleton or write out the structure of the equation that I'm aiming at, and then I can just go in and fill in the blanks, like by putting this 9 in here, I think that's very useful. So I will continue to recommend that you do what works for you. Translations of parabolas. So now we're shifting this thing around. We're changing the location of the vertex. You'll notice these two diagrams are depicting the vertex as located at h, k, and that's based on this format for the equation. So very similar to what we were seeing previously, but modified by now having a k value and an h value, or an h value and a k value. So we're going to have to be careful which one's which, depending on whether it's associated with x or y. Let's look at this first equation. I've got a y squared, x equals y squared. That's different than what we're used to when we first learned about parabolas, so this one must be opening sideways. So let's write a little note maybe. Y squared implies concave horizontal. Barely legible. Thankfully I'm narrating as we're going along. The 4 that's here, this is 4p. So 4p is equal to 4, which is greater than 0, therefore concave in the positive horizontal direction. All right, how many multiple choice options or options over here do we have that open in the positive horizontal direction? Only one. So this equation must match up with this parabola. The downside to formatting the presentation of this material in landscape like this is I can't actually fit all 4 of these equations on the screen at the same time. I can't, well, I could do this, but as soon as I'm just sort of pinching to zoom out, but as soon as I let go, it pops back in. So I'm going to have to scroll up and down. My apologies. The other thing that we don't really need, because we already narrowed it down using the direction of concavity, but let's just glance at the coordinates of the vertex. Well, let's actually do that. Because I've written so much stuff up here already, let's have that conversation when we look at the next equation. In the next equation, this actually says x minus h squared equals 4p times y minus k. All right, what's my h value? This says positive 1, this says minus h, that's confusing. What if I told you that this doesn't say x plus 1? This actually says x minus negative 1. Well, minus subtracting a negative number, that's the same thing as addition. Okay, yeah, so I see how those two things relate. And then I'm seeing my, oh, that's a very wide line. Let's try that again. If I match up my pieces, I can see that my x variable matches, now the minus sign matches, and it looks, it's a lot more clear that my h value is a negative 1. And there's the square. Strange to match it up that way. Maybe it has not been presented to you that way before, but what ends up happening is, well, I don't even want to circle it that way. I'd want to circle it this way. H ends up being the opposite of what you might think it's supposed to be. It looks like my h value should be a positive 1, but it's actually a negative 1. So the vertex here, which is located at h comma k, has coordinates. Now the h value is associated with the x coordinate, which is here a negative 1, and our y value, or our k value, is associated with the y value. And again, we have to be really careful because our k value is the opposite of what it appears to be. Our k value is also a negative 1. So maybe this is a way that you could be narrowing down your options if you're in a multiple choice scenario, but really to have the understanding of how to graph one of these on your own, being able to determine where the vertex is pretty important. So our vertex is at negative 1, negative 1. That is not, oh, this is an option. Not that one, not that one. Oh, we got to be careful because this is option 2. This vertex is also at negative 1, negative 1. So it turns out that we're going to need to look at concavity also. So let's talk concavity. This second equation that we're looking at here leads with an x squared. So x squared tells me that it's concave in the vertical direction. The 4p value is equal to 4, which is greater than 0, which means that it's concave up. In other words, in the positive vertical direction. And there's only one parabola that's concave up. It's this one, and it helps us to confirm, knowing that the vertex was supposed to be at negative 1, which it is. All right, let me give you the answers to these last couple. HK here is located at negative 1, and x squared says concave vertical, and 4p is equal to negative 4, which is less than 0, so it's concave down. So our third equation matches up with our fourth graph. And here, h is equal to positive 1, k is equal to positive 1. Notice that in equation number 3, this is leading with the x variable, but here it's leading with the y variable. So it turns out, or just remember that y is associated with k, and h is associated with x. So the presentation of these equations could put your x variable or your y variable first or second. So just be careful with how you're orienting those. So our vertex is at 1, 1. It's leading with y squared. So it's going to be concave horizontal. I'm not going to write that down. You can write it down, concave horizontal. And our 4p value is negative 4. So it's going to be opening in the negative horizontal direction, in other words, to the left. All right, for some of us, that might have been kind of painful because, after you did the first example, you're like, yeah, okay, I get it, the h and the k, and I remember, so hopefully you just fast forwarded through that. For those of you who just finished watching and taking very detailed notes on all 4 of those examples, and you're pausing, rewinding maybe, great. I'm so glad that you did that because each person learns at a different rate. Some of us need a lot more repetition than others. When I was studying math, and I mean like all the way through graduate school, I needed a ton of repetition. So don't hesitate to go back and watch these and listen to them and take notes on them repeatedly and then take notes on your own notes. Got to do what's right for you. All right, in the previous section, I think it was in 9.2, we were completing the square. Here we're going to have to do that again. So let's just do one quick spin through completing the square. Well, this is nice. Our terms are already organized according to the variables. I'm going to be adding something to the left hand and therefore to the right hand side of this equation. So I've got a couple of blanks there. To determine what gets added in there in order to complete the square, I'm going to take the 6, divide it by 2, square the result. That's 3 squared is 9, so I'm going to add a 9 here. Therefore, I'm going to add a 9 over there. Alright, so I've added my 9 to both sides. Now I'm going to factor this part of the left-hand side, or this expression. I'm going to turn that into x plus 3 squared. You could FOIL that out to confirm that that works. And then I like to put a little note over here to the right of this equation. Well, first of all, I could have written factor, because I did that on the left-hand side of the equation. But typically what I put over here is something that I'm going to do to both sides of my equation. I'm going to subtract 8y from both sides of my equation, and I'm going to subtract 1 from both sides of my equation in order to get rid of the 8y plus 1. When we do that, we end up with a negative 8y on the right-hand side, and 9 minus 1 on the right-hand side leaves us with a positive 8. Then, in order to go from the line that I've just written down to the next line, I'm going to factor again. A little different factoring this time. The left-hand side of my equation, excuse my sloppy handwriting there. There we go, x plus 3 squared. Still terrible handwriting. If you've never written on a tablet with a stylus, or in this case, I'm on an iPad with the Apple Pen, not easy. The pen is just so slippery, it just slides over the surface, so it's tough to get it particularly accurate. The factoring that I'm going to do on the right-hand side is out of these two terms on the right-hand side, I'm going to factor out a negative 8. So the factoring that I'm doing over here is more like reverse distributing. And be careful the sign change there. Negative 8 times y would equal negative 8y. Negative 8 times negative 1 would make the positive 8. So the double negative makes the positive. You can always multiply back out to make sure that you factored correctly. This is standard form for the equation of this parabola. My h value is hiding in here. It's negative 3, right? The opposite of what it looks like it should be. My k value is associated with the y variable, the opposite of what it looks like it should be, so the k value is a 1. Also, my 4p is equal to negative 8. If I take the absolute value of both sides of that, I find that the absolute value of 4p is equal to positive 8. And I think the only reason I really love that is, well, a couple of things. It means that the absolute value of 2p is equal to 4, and the absolute value of p is equal to 2. Now let's go and use all of those numbers. Let's use this number, and this number, and this number, and this number. And let's use the fact that it's the x variable that's being squared. Oh, and let's use the fact that 4p equaling negative 8 is less than 0. Alright, so there are a lot of things that we're using in order to graph this thing correctly. Let's see what we get. Where's the vertex? The vertex is located at h comma k, which in this case is at negative 3 comma 1. So let's plot a point at negative 3 comma 1. There we go, that's our vertex. And the distance to the focus is p. With the absolute value of p, which we said is equal to 2. Now, this parabola, in which direction is it concave? Well, we said that the x is being squared, like y equals x squared, so it's either opening up or down, and our 4p value is -8, which is less than 0, so it's going to be opening in the concave negative vertical direction. In other words, concave down. And if our parabola is concave down, don't draw that, then our focus is going to be below the vertex somewhere. So starting from our vertex, let's come down 2 units, because from vertex to focus is 2 units. That's a distance of p. So there's the focus. I put a little f there. I'll put a little v above the point for the vertex. And remember that the lattice rectum has a total length of 4p. 4p is equal to 2p plus 2p. So from the focus, I'm going to go a distance of 2p, which is 4 units, to the right. 1, 2, 3, 4. That's one end of the lattice rectum. Back to the focus. 1, 2, 3, 4 units to the left. That's the other end of the lattice rectum. I'm going to start drawing from the vertex. Come out here through that end point. Back to the vertex. Out here through this end point. And I've got myself a pretty darn accurate depiction of this parabola. Again, that was a distance of 2p. That's how I knew where to draw those 2 points. Now my f is in the way. There's 2p. And then this distance, tough to get it in there, was p. The other thing that's missing from this diagram is the directrix, or from this graph. The directrix is also going to be 2 units away from the vertex. Remember, I described it as being behind the parabola, or away from the concavity, you could say, maybe. So that's our directrix, and let's just put that information right on the graph. Directrix, the equation of this directrix. Again, this is how I remember horizontal versus vertical lines. This point on the directrix, and this point on the directrix, and this point on the directrix. All of those points have something in common. They all have the same y value. The y value is 3. So that's the equation of your directrix. A little hard to read because I wrote it right on the axis there, but it does say y equals 3. And up here we have the equation for our parabola. If you wanted the coordinates of your vertex from your really nice graph, I think you could get the coordinates of your, coordinates of your vertex were easy. That was the h comma k. But if you want the coordinates of your focus, pretty easy to count down 2 units. If you want the coordinates of the endpoints of your lattice rectum, you can count your way out. Even if you weren't graphing this thing on an actual piece of graph paper, you could still draw it, sketch it pretty accurately, label everything. You could still have things like these, the 2p and the 2p, and as long as you know that total distance and the location of your focus, you could still do some arithmetic and find out the coordinates of the endpoints. You can do it, just do some detailed diagramming. All right, that is all I'm going to say about parabolas. I think that's plenty. Thank you so much, and I will see you for the next section, section 4.